I will have to tell you that I am very poor at getting my talks done on time. And so people usually find that I'm on the airplane uh, working furiously on getting those last few slides done. And so knowing that I was going slowly, one of my longtime collaborators, Greg Werner, who's on this talk, said he was wondering if he could help me out by fixing up a jet noise generator next to my office. That didn't have to be the case, so here I am. So I'm going to talk to you about something that we call Sleptic, which is speed limit particle and cell. And the people who have been working on this are Joe Tice, Greg Werner, and Tom Jenkins. Greg's at TechX. I'm sorry, Tom's at TechX, Greg and Joe are at the university. And this is going to be talking ultimately about particle and cell methods, which are very powerful for kinetics, but they can be limiting, especially when you want to do ion scale simulations with kinetic electrons. So what Sleptic does is it provides an explicit method that eliminates that disparity. And I say that in air quotes because you'll see later that there are some issues with the explicitness that we're going to have to work around. But what it does is it captures the required processes while ignoring the unimportant processes. And it can be solved by particle methods, and it's been shown now to work on sheath and breakdown problems. This is the subject of Joe Tice's thesis. So, let's see here. My next slide is not working, so I'll do this. So I just wanted to, I had to balance out what Paul said at the beginning. He said that I worked at Los Alamos, and I just have to balance out Los Alamos and Livermore. I don't want anybody to get upset after all. And so I have to point out that I actually was born in Livermore, March 15th, 1953, at St. Paul's Hospital. And I was delivered by Grace Devnich, which, as you see here, was the Tri-Valley's first woman doctor. So therefore, I would almost claim that I was supporting gender equality from the very beginning, except I actually didn't have a choice on being born, and I actually didn't have a choice on choosing the doctor either. But there I was. And I don't know if you guys have ever heard of something called the California Research and Development Corporation, but that's where my dad worked for all of 3 months before I moved on. We had a large amount of interactions with Livermore. Used to, in the 70s in grad school, we had joint seminars with LBNL and Livermore. That's where I got my degree. In 2010s, we had a nice big collaboration called Facets. It was actually in 20-aughts and then went to the 2010s. And now maybe I'll be a visiting scientist, but we don't know because the lawyers are not responding to questions about IP. So anyway. So who am I? What is TechX? Well, as noted, I'm a professor of physics, and I'm the CEO of TechX, and TechX builds computational software. Our main package is VSIM, which is a structured mesh cut cell electromagnetics, particle and cell, DSMC, fluid, and we're porting it over to GPUs and AVX and stuff like that. We also have USIM, an unstructured mesh shock capturing, RSIM, an emerging radiation modeling code, and it's a kind of code that can do sort of allow you to work with CAD tools and then be able to do radiation modeling with them. We have customers and collaborators all across education. West Virginia, for example, is teaching a course this fall using our tools, gets the students up to working quickly. Government, CERN, previously LLNL was a customer. Hope they get them back as a customer again. Industry, Applied Materials, Boeing, and others. So basically, it makes things easy by providing people a GUI and setting up problems for them in a visual way. But what I want to talk about today is electrical breakdown in complex shapes. And this has a wide variety of applications. One of the things you would like not to have is tank farm fires. They're very hard to put out. The other thing is you would like to have a nice electrical power distribution. And when these things happen, it can burn up your circuit breakers and rectifiers, and you'd like to be able to understand how they will happen, hopefully design things with the shapes that are needed so they don't happen. Electrical discharges are used in nanoparticle generation. They're used in plasma medicine. And of course, we have them in undergraduate labs, although I always worry about undergraduates using things like that. So let's just look at one of these problems for a minute. Here's the oil tank problem. In the oil tank, you have a wall over here. This is the outer wall of the oil tank. And the top of the oil tank is floating. It's actually a big hunk of metal, and it has some pontoons underneath it, kind of thing. And it's got this ladder, so you can come up the ladder that goes around the oil tank and then climb down on the roof as you need. The important thing, though, is as the oil, as it's filled or lowered, this floating roof goes up or down. And, that keeps the roof right on top of the oil that you're trying to protect. And the issue is that you have to have a gap between this metal and the sidewall of the tank. And this gap is then they put in a rubber gasket kind of thing here so that the whole thing can float up and down. Now what happens in the field is that lightning hits the outer wall typically because it's the highest thing here. And that by induction creates an electric field between the wall and the floating roof. The floating roof is a big hunk of metal sitting on top of a dielectric, namely oil. And so what they do is they put in shorting straps between the wall and the roof. So they have these straps that come down and hang down and touch the roof. Well, actually, there's a shorting strap here. No, I've forgotten. In any case, the gap is of order of tens of centimeters. The shorting straps are a few centimeters in width, and the tank is roughly 30 meters in diameter. And you have to simulate the whole thing because it's inductive and you have long-range fields. And the question that comes about, and we were asked by a company called Lightning Eliminators here in Colorado, and one thing about having a company is that you don't just stay sort of focused on one problem all the time. Somebody says, hey, can you tell us how many lightning straps we're going to need to keep the voltage down between the floating roof and the walls? And of course we say yes. All depends. How much money, right? We'll do it. We got people who can work. Ultimately, the proposal was made to the American Petroleum Institute, and it was quite an experience. I know most of you are used to going to Washington and going into Department of Energy and sitting down with other people. I went and sat down with a bunch of people. As one of the guys said to me, you got to keep in mind that a lot of these guys just changed from their mud-covered boots because they were out in the tank farm to their better shoes to come and listen. And that was interesting. But ultimately, it was not successful. I was not able to convince the American Petroleum Institute that they needed high-performance computing, and in particular us, to solve this problem. But it's a motivation, and we may come back to that. One of the things we could not do at the time was do the full range of collisions in that problem. So let's go back to how breakdown occurs. So breakdown's been known a long time. Paschen, 1889, breakdown voltage is a function found empirically over here on the right. Where's my mouse? There it is. Found empirically over here on the right that, excuse me, my mouse. There we go. My mouse goes over WebEx and it sometimes disappears. There we go. So what happens is that he found empirically that there was a minimum in the breakdown voltage as a function of the pressure times the distance. But the important thing is that it depended on only the pressure times the distance. And the point basically being that if you make the thing too short for a given pressure, the electrons can't ionize more electrons on their way from the cathode to the anode. And if you make it too long, the electrons lose energy, or too much pressure, the electrons lose energy to elastic scattering and they don't keep up the energy needed for ionization. And there's a minimum right here. In this particular case, from Arthur Phelps, who was a member of JILA here at the University of Colorado, the breakdown voltage in argon here, it's for 1 torr centimeter is somewhere between 100 and around 200 volts. So what's the physics? Physics has long been known too. Basically, electrons are around, something gets this thing going. They're accelerated from the cathode to the anode. As they're accelerated, once they pick up an ionization energy, they can ionize an argon. Now you have 2 electrons and an Ar minus. And if that was the only thing that happened, these electrons you'd have a exponential growth of them, and then they'd hit the right-hand wall. But critically, these argons now get accelerated the other way, and they hit the cathode, and by secondary emission process, they release more electrons. And so you can say very simply that if the electrons going to the right release an average of gamma electrons, and then if the electrons accelerated to the right release alpha ions, and if those alpha ions then when they hit the left release gamma electrons, then if alpha gamma is greater than 1, the current grows exponentially. The process time, the time it takes this process to occur, is basically the time it takes those argons to get back, because they're fueling the process. It's not the time for the electrons to get across. That's really quick, but more electrons don't get produced until those argon ions get back. So we understand this very well for plate geometry, but what about tank farms, high voltage circuit breakers, electrostatic accelerators, and all these other things? Well, that's very difficult, because those are complex geometries. And if you have a complex geometry, you really got to do the whole calculation. There's no nice, simple analytic answer like you can get in a parallel plate capacitor with gas in between. So you say, well, let's just code this up and get the answer. All right, what do we have to do that? Well, kinetic modeling is critical, but it's limited. The electron distribution consists of electrons going through the gas, and then they occasionally ionize and they lose, whatever it is, 13 volts in hydrogen, something like 20 in argon. My memory is not good at remembering all those kind of things. But then as they go to the right, then some of them get up to a little bit higher energy, and then they ionize a little later, and then they lose their energy a little later, and so on and so forth. And so you have a very non-thermal distribution, and you're not going to model this very well by fluid theory. And you need to model complex shapes with scale disparities. And you need to model this for several ion transit times. That is to say, the physics recirculation time. Because it's a complex kinetic modeling case, and the distribution function is really quite complex, it's kind of tailor-made for particle and cell methods. But particle and cell methods have a problem in that in a particle and cell method, you need to pick a time step that is smaller than the time it takes the electron to cross a cell. The accuracy of particles in cell relies on the fact that when you evaluate the force on the particle, you do a good job. And so if the particle moved over a distance where it felt a whole bunch of different forces, you would not be getting an accurate force on that particle. Okay. Now, let's see what that means. Now, as we've said, particle and cell is very good. What you do is you represent your charged particles by macroparticles, and they interact with the electromagnetic field. More on this later. I like particle and cell for this kind of modeling because it provides a representation of a complex velocity space with a minimal number of degrees of freedom. You don't have to grid up all of velocity space. You instead more or less count on having a Monte Carlo representation of velocity space that over many cells ends up providing sort of thousands of velocity space points. And particle and cell has, of course, got a long history going back to the 60s. And there are many advances in it dealing with noise, numerical restrictions, and so on. Now, of course, at some point you want to give up. If you end up having thousands of particles per cell in 3D, you might start thinking about going to a continuum representation. But for this problem, it's good. Let's keep in mind a couple of things on its restrictions. One is the one I just mentioned before. A particle cannot move over many grid cells in a time step, or else you get an inaccurate force and you provide an inaccurate current or charge. Next, you have to have the so-called plasma Courant condition. You have to resolve the plasma frequency if you're doing explicit, otherwise you get a strong instability. 3, there's something called the Debye length resolution needed to prevent the grid instability, which tells you that the space has to be small compared to the Debye length. These are all very related. In electromagnetics, there are more things. All the simulation experts here, I'm sure, are well aware of the pain that some of these things cause. Now, these things are not related. These are numerical restrictions. They're not related to resolution requirements. So for example, if I want to do cold plasma oscillations, the wavelength determines the physics, not the Debye length. And yet, if it's slightly warm, we have to resolve the Debye length for stability. If we're doing MHD, the electrons around, if we wanted to do MHD timescales, the electrons around mostly just to cancel the electric field. So we don't need to resolve the Debye length, and yet if we did it with particle and cell explicit, we would have to. If we're doing ion acoustic modes, once again, the electrons now have to be kinetic, remember, because they're a Boltzmann response. But the wavelength is very long compared to the Debye length. If we do plasma sheaths, we're doing a kinetic situation, but it's not perfectly thermal, right? Because the electrons going in to the sheath don't come back out. So you get these chopped electron Maxwellians. And if you're doing plasma discharges, which is what we're going to talk about today, the only thing you need to resolve is the ion crossing time. And you need to resolve the mean free path, which is needed for so-called direct simulation Monte Carlo. So we have limits to this that are not related then to the physics. Now, when we do particle methods, we basically start off with the Vlasov equation or Liouville's equation, or what do you want to call it? You know, it's the standard d by dt plus, in conservation form, gradient of the flow in x space plus gradient of the velocity gradient of the flow in velocity space. And you can solve this by particle methods by saying, oh, let's put a bunch of particles of given weight and delta functions in their position, and you derive how you can make the solution satisfy either one of these equations. And you can say WP is constant, and then as long as these things follow the trajectories given by the forces in the system, you have a solution. So you're off to the races. You discretize this system, you put it on a grid, you add fields, do the field solves, and that's particle and cell. That's your basic idea. All right. But now I want to consider the case where I have something very slow and my particles are moving very fast relative to it. So let's consider a resonance here in phase space with a phase velocity that's very small compared to the velocity of some particle up here. Then what happens is, because this particle is moving fast compared to this resonance just looks like it's almost static to that particle. And so this particle just races along over the resonance. And in essence, the particles at this high velocity are essentially in equilibrium with this perturbation. And so for those particles, the time derivative can be ignored compared to all of the other terms in the equation. So that's what we're going to do. It's a simple ansatz. It's so simple, you ask, why isn't everybody doing it? Okay, so now I'm going to say that that function, that velocity space function, is some function that I'll call beta, our slowing down function, times another function z. And this is where you're going to watch for the sleight of hand. I'm going to write down the equation for beta, for g, by putting it in here, beta g, beta g, beta g. And then I'm going to take the time derivative of beta g, and I'm going to say, I'm going to add a term, which is d by dt of g of t, and I'm going to subtract that same term on the right side, add the same term to the right-hand side over here. And that original beta g term, I put over here too. And now here's the trick. I'm going to choose beta such that for slow particles, beta equals 1. So the right-hand side vanishes. And for fast particles, I'm going to make beta z tend to 0. So the right-hand side is unimportant compared to the left-hand side. Phase-based derivatives, none of this becomes important. So in both cases, I can ignore the right-hand side. If I'm at high velocity, you see, while this term is here, it's dwarfed by the higher velocity term over here. V is the dominant term. So really at high velocity, I'm balancing these two terms. And at low velocity, I have the whole equation. And so putting all that together, I just get a new equation for g, which looks just like the Vlasov equation, except that the velocity is multiplied times beta, and the acceleration is multiplied by beta. And so the distribution evolves as if both the velocity and the acceleration are slowed down by beta, which is to say fast particles are slowed down, slow particles are unaffected. And here I go losing my mouse again. There it is. Okay. Now, other than that, you got a lot of freedom in that prefactor. You can choose that beta such that for slow particles, beta equals 1. That's what we want. And for fast particles, beta goes to 0. So the right-hand side becomes unimportant with the phase-space derivatives. And here's a couple of examples. Here's an example, is that beta is just V naught over V naught plus V squared. And that says beta V is V over 1 plus V over V naught squared. So when V goes to infinity, this just becomes V naught, and when V goes to 0, it just becomes V. And we have great discussions here about how to choose beta, and I'm usually on one side, and everybody else is on the other, and that usually means that I'm wrong, but nevertheless. So there's also no limitation on how you choose beta. You could choose beta to refine it in some regions where you want to have more refinement of your simulation. You could choose a smaller beta there. And you could increase beta in time when faster phenomena appear. We haven't explored all those things, but it looks like all those things could be used. So the Sleptic equations, they're just like the Vlasov equation, except with a different velocity and a different acceleration. And so you can solve them in the same way. You solve them by following trajectories, except that now, when you go back to actually put in something in your charge equation to solve Poisson's equation, for example, you have to take into account that the real velocity, phase-space velocity, is beta times this one. Now, what does that mean? That means, hey, if I slow down these particles, I would have more of them in the simulation. So I have to counteract that effect because, that's just flux conservation. So if I slow them down, I have to give them less weight. And that makes the density work out. Now, I say this because I talk about particles. I think about particles a lot. But there's nothing to prevent you from doing this with a fluid equation. It would, for example, help in certain problems where you need to do an implicit solve in velocity space, because the less things change, the easier it is to come to your solution, even in implicit cases. Now, this is an important point, and people always get a little bit confused on this. I'm not making a coordinate transformation here. I'm not changing the way particles move through space. That's what a coordinate transformation would be doing. You'd have different coordinates, and you'd have different equations. It's not doing that. This is not a delta F approach. That particular WP does not change in time. The weight associated with the particles, because of them having been slowed down, does change in time, but you're not separating this into a background and a delta F solution. And as I say, it's not even a delta F approach. You could use continuum methods with this. So Sleptic is simply an ansatz that allows one to treat fast particles as if in equilibrium while treating slow particles exactly. And it fits pretty well into the DSMC pick cycle, almost, a little bit more later. You do a field solve, particles, you interpolate, get the forces, you accelerate with a modified acceleration. By the way, there are some pointwise implicit algorithms in solving because, I won't get into those details. But anyway, you can do that. That's a pointwise. Then you move, and you always move less by beta. And you deposit. You have to put beta in there, and I'll talk about this more. And then you put in collisions. So, piece of cake. All right. So now I'm going to have to tell you a little bit about some of the dirty laundry here. The weight variation actually does cause a problem. So remember I said the distribution function had this beta in it? Well, let's go back to how we solve things with leapfrog stepping in standard electrostatic pick. We would know the positions, say at the full time steps, and therefore we would know the potentials. From the potential, we'd get the gradient. From the gradient, we'd get the force, and we'd advance the velocity to the midpoint. All right. Now we know the velocity. We know beta. Beta is a function of the velocity. But now we need beta over here because we need to know how to get the weight over here, because the chart, we'll call this the charge density weighting, and we don't have that beta over here until we actually advance this and then take a half time step back, and we can't advance this until we know phi in order to take its gradient, et cetera, et cetera. You see the problem, the usual implicit business. So we need the charge weight for weighting, but we don't know it. I'll come back to this later. It is similar. The ultimate solution, we again are arguing at this middle part of the country on how to do this. But I will point out that this would not be standard implicit pick even if we did this, because in standard implicit pick, what you're trying to do is solve things for very large cells, but you still keep the fact that particles don't move more than very many cells in one time step. Here, you're keeping small cells, and you're shrinking down the amount they move in one time step. So implicit pick by itself would not solve this problem where our cells need to remain small to resolve this physics. We're still resolving Debye-length physics in this particular case. So it's different. Now, there's one other complication, and that's what's the so-called current weight. The current weight, it's the name we give it, it's the rate at which particles cross the surface. Well, the rate at which they cross the surface is still that function, beta, because the amount that get to the other side, and then if you integrate them times their charge weight, is equal to the amount that crossed given by beta. So when you do collisions, you have to make some little modifications to the collision rate. I won't go through all this. It depends on all the details of direct simulation Monte Carlo. And but you have to be careful to get the rate of production correctly, because collisions are kind of like fluxes, right? The number of particles that come into a collision better equal per unit time, better be equal to the number that come out. And so when you take the collision rate in Sleptic, instead of just the usual one where you would have just the relative velocity times the cross-section, you have to put in both of these beta factors, and then times the regular weights. So let's not worry about that, but let's just point out that that's a complication. And you have the same issue with wall interactions. Obviously, if an ion goes into a wall and causes an electron to come off, you don't want one ion with a secondary electron yield of a half producing more than a half of an electron, probabilistically. So we've been through the verification studies on this. We've compared it with particle and cell, and after getting all those things right, it actually works. And so now I'm going to show you some results on validation, i.e. comparing with experiments. This is really the work of Joe Tice, one of my grad students, and heavily the work of Greg Werner as well. Greg Werner did the implementations in the code. Joe Tice has been working on getting the simulations to work. So let's go back to that problem that Art Phelps was studying. That was argon, okay? And what we do is we initiate argon discharge by emitting a small amount of electrons from the cathode. We have put in ionization, elastic collisions, various combinations of excitation collisions until you get the right answer, which I think is really only the first one. And we put in secondary emission for the argon minuses coming back to the wall. And the yield we put in was what Phelps had in his paper, 0.07. That's a very hard number to really know, but we did what they did. And the energy gain, of course, is from the voltage. Now, in this problem, the mass ratio is pretty darn big. The mass ratio of argon to the electrons is 270. So you have to resolve that the argon velocity times the cell size, which is this, has to be less than the argon velocity, which is this, times the time step has to be less than the cell size, and the electron velocity, which is this. So the electron condition ends up giving you a numerical condition that is 270 times stronger than what you really need. So we went back and we resolved this 219 cells across 1 torr of argon with a 1 centimeter gap. And of course, this is all computations, not experiments at all. The experiments we got from another paper. And the numerics, we follow it temporally. And what we do is we simulate for 10 ion crossing times, and we look for exponential growth. And the time step, remember, for PIC is the cell size over the maximum electron velocity, would take 4.7 million time steps. But with Sleptic, it only takes 17.5 thousand time steps, i.e. it's a savings of 240. So back here I have our code. I think it's all set up. I hope I got this right. Pressure torr, yes. And I'll just go ahead. These are the conditions there. I'll just go ahead and run this. This is always dangerous. See whether it's going to crash. And if it does crash, I have one that didn't crash over there. So while that's running in the background, we'll just go on and talk about some of the answers. So as I said, you go out for the same amount of physical time. 10 ion crossing times is about 30 microseconds. And this is what happens at 170 volts. It amplifies, it starts to saturate. This is what happens at 180 volts. It exponentially increases. Now, we don't want to do the exponential increase all the way out. We just want to figure out where it's going to break down. So we stop these simulations after a reasonable number of ion crossing times and see whether it looks like it's an exponential or not. And this is our result for the Phelps case. At 1 torr, the breakdown occurs somewhere between 170 and 180. And that's that red dot right there on that graph. So now we've at least got 1 point of validation. And we're now starting to believe that we might have a tool here that would be good for a certain class of physics problems. No tool does everything, but for a certain class. Okay, this is on Joe's machine. The Sleptic simulation of about 17,000 steps took 64 CPU minutes. The PIC simulation took 84,000. He actually got a different number from me, and I'm not sure what's going on. Okay, this simulation's off and running. Good, didn't crash. It's always dangerous to demo your software in front of anybody. We actually observed a speed up of 130x, and I told you it was 270 times fewer steps. So what that means is our steps are more complicated. They're twice as computationally intensive as PIC steps. We haven't done any performance optimization or maybe other ways to formulate the problem. We're looking at that. PIC, of course, has been studied for, what are we on now? 55 years or something, actually even longer if you go back to Frank Harlan's work back in the early 50s. So there's been a lot of thought about that. We need more thinking about Sleptic. Better not take 50 years because I'm not going to be here. But we are doing some performance optimization. So it's complicated. It didn't get the full speed up, but it got a significant amount. So what I want to tell you then is it should give you some big gains in computational speeds if you can say that the most important velocity is very small compared to your electron velocity. You don't need to resolve the electron plasma oscillations. It's especially good for TE greater than TI, large mass ions, and examples of plasma sheath. We're having some issues with free expansion. We think it ought to work for plasma thrusters. And as you've seen, it works for the capacitor breakdown problem. Now, I think I'm going to jump down here since it looks like I have a little bit more time than I anticipated. Maybe not. And just point out one thing here. That it has a different dispersion relation. If you go back and you solve for the dispersion relation for these modes in Sleptic, and I won't go through all the math, but you've all done the Landau analysis, I'm sure. What you find out is that the plasma frequency of the electrons is slowed down by V0 squared over VE squared. Because some of you might have been wondering, well, if you still had the omega p delta t restriction, why didn't you get killed by that? And why didn't your simulation go unstable? And the answer is omega p for Sleptic particles is smaller by exactly that slowing down factor. And Tom Jenkins is working on a paper that's going to go through this dispersion relation analysis in detail. All right, so coming back to here. Actually, I'm curious. Oh, it finished already. Look at that. So, just to put this in perspective, and I don't know why my answers are so much faster than Joe's, I am on a 4 gigahertz machine. This is no parallelism, but you can see here that this thing started at 1237 and it finished at, and I'm sorry, these numbers are probably too small for you to see, at about 1242. So it took about 5 minutes. If we were using regular pick, that would be 130 times 5 minutes. And let's see, there's 12 times 5 minutes in an hour. So it would be 130 over 12. It'd be more than 10 hours. Did I have that right? Yeah, it'd be more than 10 hours. So the good thing for you guys is that you only had to watch my simulation for 5 minutes, and otherwise you'd had to be here all day. Lots of directions that we're thinking about going to. Combine with implicit to get that problem for the self-consistency solved. We're looking at including strong magnetic fields. There's a problem with Sleptic and magnetic fields, and remember, it slows down everything. And so, in fact, it slows down the cyclotron frequency. We're trying to think about how we do that. And then, of course, we want to combine it with all the usual things, computational devices, multi-mini core, AVX, et cetera, et cetera. So after B&B, it's time to do some new physics. And we're just getting started on this, but I think what would be really cool would be to show that we can use this to do a complex problem. Let's do this on the breakdown of something where the shapes come from something like CAD. We have all the stuff built into our codes, right? We can put in shapes, we can do the cut cell meshing, somebody can give us a design from SolidWorks, and we can make it work. So we're interested in finding people who need such problems solved, and maybe we can do some sort of working together to see what can happen. Now, I realize that, I've talked a lot about the work that Joe's doing, but I also want to tell you a little bit about some of the work that my other grad students are doing, because I do have 5 of them now. Is that right? And I want to give them a little press. So the best press I can give you is maybe showing you their pictures. The old guy in the upper right, of course, that's me. And then we have Luke Adams, Jesse Snelling, Catherine Woolfinger, Joe Tice, and Ryan Lau. And Jesse, Catherine, and Joe have been working with me, and Greg, who's my longtime collaborator. We have published many papers together. Greg's over in the lower left, middle left, published many papers together over the years. And Ryan is not precisely working for us. He is actually your employee, and he's working there this summer. So you can go hunt him down if he's around during COVID times and actually have a conversation with him about what we do out in Colorado. And Luke just started with us this summer, and he's doing some algorithm stuff. And I'm going to tell you, I've told you what Joe does, and now I'm going to tell you what Catherine and Jesse are doing. So here's what Catherine Woolfinger is doing. She's looking at low-density plasma formation. And the issue with low-density plasma formation, let's see, somehow this got a little bit too big, is that what you'd like to do is create plasma channels so that you can focus laser pulses to do laser wake field acceleration. And there's some interesting work out recently by Shalou of 2 years ago, where they start taking, what you'd really like to do is go to very low plasma densities, because the single stage gain in a laser wake field accelerator is basically scales with the laser frequency divided by the plasma frequency squared. That gives you with some coefficients, the final gamma of the situation. So if you could lower the density, you could get a final energy that's larger. It'd have to be longer because your gradient's lower, but nevertheless, you could do that. And so people have been exploring, well, what do you do to make these things? And the classic thing has always been to create them by a hydrodynamic process where you dump a lot of laser energy into some location. It creates a shock wave, an explosive shock wave, going outward, not inward. And you end up with a hydrodynamic expansion of the plasma columns, and you end up getting this bunching up out here, and that gives you your laser wake field channel. But lower density plasmas are going to require a different method. Shalou pointed out, I didn't put up his plots up here, the whole channel seems to be going away. And of course, actually, the whole technique of doing these simulations goes away because you can't use hydrodynamics at 3 times 10 to the 16th, or what we're doing here, because it's not hydrodynamics. It becomes collisionless. You have to use something like particle and self. So what have we done so far? And this is Catherine's thesis. And please don't steal any of my students before they graduate. She's been doing 2D PIC simulations with a single laser pulse. And we've already observed some very interesting things. The first thing is that the density profile is absolutely flat. No channel forms. Not surprisingly, there's no hydrodynamics. But we also observe something else. We observe an electromagnetic pulse propagates out from the initial interaction, and we can use that electromagnetic pulse backwards as a way of detecting the laser intensity, as well as the radius and the amount of plasma that has been created from the ionization process. So it's kind of cool. It comes from a time-dependent ponderomotive force, the d by dt term, d by dt of the amplitude squared. And you can show that this EM pulse, even though it's generated, it's caused, and it ends up with an oscillation at the plasma frequency. And Catherine will be presenting some of that stuff at the virtual Division of Plasma Physics meeting this fall. So that's one area we're going into. And then another area that we've gotten interested in is nano vacuum channel transistors. And the idea here, and I've shown the thing that Jesse didn't want me to show, but anyway, I wanted to show this one because I think it's prettier. What's happened now is, of course, all these years of transistor technology have told us we can make really tiny things. So when we were doing vacuum tubes, we had really big things, and you had to heat the emitter with a filament to make it hot enough to get, I guess it's Richardson-Dushman emission off of the filament. And then, of course, you're heating things up and cooling them down and heating them up and cooling down, and we all know what happens. Those of us who are my age know that what happens is that every Saturday, you bag up the broken vacuum tubes from or every few Saturdays, you bag up the broken vacuum tubes or the vacuum tubes from your TV, trying not to get shocked by that huge capacitor next to the CRT, throw them in a bag and go down to your drugstore and put them in the vacuum tube tester, and then finally you bring them back and get your TV working again. We don't have to do that now. Lithography tells us we can make very, very tiny things. Here's an example of a device there on the left where there is a emitter tip radius of 10 nanometers. Now, we all know that stuff starts to come off of materials at the gigavolt per meter, which is the atomic electric field. If you now, or the work function, kind of like over its distance, if you now say, well, I have something really, really tiny, I don't need a big field. It just comes off with cold Fowler-Nordheim emission. If it's at 10 nanometers, and that's the radius, you get some enhancement there, and, a millimeter away, which is, 10 to the 9th nanometers, you put a volt, and you got a gigavolt, or you put 10 volts, and now you get field emission, and now what you can do is you can surround it with a little hole, and you can make a gate, and you end up with a field effect transistor where it's all in vacuum. And why this is interesting is because it's radiation hard immediately. You can't hurt vacuum. Okay, not until you get to the Schwinger limit anyway. You just can't hurt it. So, and you don't hurt metal very much. When transistors have radiation problems, it's because radiation comes in and causes electron hole pairs and causes breakdown. But there's a problem here. Like I said, I need nanometer tip, and I'm going to put my voltage over a millimeter. Okay? So I somehow have to resolve nanometers in a millimeter. Well, that's 10 to the 9th, and people don't do that every day, but we are developing a couple of really cool approaches, and I'm showing the one that we're not necessarily working on so much now, but I did want to show you and brag about our new meshing capability, which shows that we have meshes that resolve these nanometer tips down here with very fine cells, and it's kind of hard to see over here, but they're cells that are of order nanometers. And then we vary the meshing in a continuous way, and we can cover this whole range of the nanometer tip out to the millimeter. And that would be, a millimeter would be, like I said, 1 billion nanometer cells. We can do it with about 1,000. And we can do the electrostatic solve on this thing. And so it's kind of cool. We're actually looking at another way, and this is part of, and this is Jesse's thesis, of actually sometimes this way doesn't work out so well because at the very beginning, the electrons, you have to pick a really tiny time step to keep the electrons from crossing a cell. Well, maybe we use Sleptic. There's all kind of things we're looking at. So that's what Jesse's doing, and I just wanted to make sure I pointed that out. Luke, I don't have a good picture for, but he's looking at some new symplectic integration methods. And Ryan is actually working with David Strutzi at your place, working on some 1D, some blast-off simulations, which I hope to be able to collaborate with as he moves forward with David. So looks like I'll be his supervisor for his thesis at Colorado, but he'll be doing most of his work with David and others at Livermore, for which he has submitted some sort of internal, like an IR&D or something. I don't know exactly what it is, but you can talk to David about that. So now let me give you the real summary. This is sort of overall a taste of what's going on in my university research group. We have new algorithms going on. We have predictions of plasma target formation, new physics discoveries. We have nano vacuum channel transistors. And at TechX, there's another 40 people, and they're doing even more. Hypersonics, particle accelerators, plasma formation. And what I'm starting to call this thing that we're in now is a pandemic. I hope this ends at some point that we can see each other in person. And so with that, I'll stop. Thanks.
Thank you very much. That was a very nice talk. So we can enter questions in the chat feature. So you can see there's a little text bubble at the bottom, and I'll read them off as they come in. I guess to get the ball rolling, I had a question about, so if you're accelerating to the ion timescale instead of the electron timescale, how do you, what physics is lost there? Like, so for example, like how do you recover ion acoustic waves? Because you need that interplay between the different species to get those.
Yeah, so in this particular case, remember the electrons are still giving the right response if it's slow, if the perturbation is slow compared to the electron speed. Because the fast electrons are just zipping over things, and we use Sleptic for them, basically continuous approximation. But then for those slow electrons, they're still following the correct dynamic. So they're still getting trapped in an ion acoustic, vortex, whatever, resonance. So that should still happen. Oh, there's Bruce. Okay.
Yeah. So Bruce Cohen asks, I missed the part where you explained how to do the time-stepping interleaving with the modification due to beta. What does the code do?
So what the code does is it just Beta is a continuous function of space, velocity, space, and time. And let's see, where's the equation? Here it is. It's just these two equations right here. We just solve those equations for the velocity and position rather than the usual ones. So it's just a different equation. You follow the trajectory like that between time steps, and then you weight them to the grid.
I have a related question.
Mm-hmm.
When do you choose the beta as a function of position before you run, or do you do it on the fly?
Right now, we're doing it before we run, and we're keeping it to be a given function of velocity. We see lots of potential for doing other things, but we have not done them.
Okay, and so the particles don't carry around their own beta. You somehow have it tied to the grid, or?
So, well, beta is a phase-based function, but in fact, when you evaluate beta at the particle position, that is the particle's beta.
Okay, thanks.
Okay, and we have a question from Rich London. Do you think Sleptic would help for high-intensity laser interaction with a solid target, hot electron generation and transport?
Right, so there's a bunch of different answers to that, and I haven't thought about it deeply enough. But one thing is that if you know the laser's there, you have to at least resolve the laser, right? Frequency. You can't ignore that if you're following that fundamental process. Now, if you're in a very overdense plasma, though, you typically don't need to resolve the electron plasma frequency. I'll tell you that I see potential there, but I haven't thought about it hard enough. I will say that after that laser has come and gone, and now that you're in the free expansion mode, let's say for the particles coming out the other side, there I do see potential, but we have run into some problems with free expansion, and so we're not ready to show any answers on those yet.
Okay, and there's a question from Alex Friedman. Are there circumstances where a particle moves in and out of an equilibrium condition?
Oh, absolutely. Absolutely. We are following the beta of these particles, and the particles can, so for example, let's come back to this problem here. If I chose my velocity limit, let's say, to be right around the top of this resonance, that would mean that if particle down here at the left, the particle that's following this trajectory that just skitters across the top of the resonance, at the very left, it's slowed down. Its speed limit, it is not slowed down. Otherwise, I wouldn't get it to follow this trajectory. But at the top up here, it is slowed down. And so this one trajectory, different parts of the trajectory would be on different places of the beta.
I think you touched on that in the earlier answer that you gave. And so do you explicitly have to evolve a debated T term in the equations, or is that a term that just happens automatically and you don't need to?
That just happens automatically.
Okay. And you'd mentioned this casually in passing to me, and I thought I'd just share my comment, which let's see if you still agree with, that what happens in systems like this is that F is constant along characteristics. And if things are varying slowly, the way you represent that F by having a chain of particles that maybe didn't move as far as they should have, but is still on a characteristic, doesn't matter. And so you're allowed to slow things down. It's just a different way of representing that same F.
Absolutely agree. Okay, so let me get to Bruce Cohen's other question, which is, how did we resolve the potential? Well, that is the $64,000 question right now. Let's see, where do I have that here? By the way, here's a nice place to point out how many of the people here have worked on methods like this, including a couple of names here that you might recognize. When we do the weighting, we do not resolve it because we're dealing with static methods. And in fact, in this particular case, it was not even self-consistent. Now, having said that, I fear that my PhD in plasma physics is going to be taken back away, but we're getting there slowly. So we do not resolve that yet. We believe that the only way that we can resolve that, that's this one, is, well, we don't have a method and we're debating those things. But one way to solve it would be to do an implicit solve where you would advance both v and x at the same time. And as I said, this would be an implicit solve, but it would not be like implicit pick in the sense that we're still resolving the bilengths. And that's where implicit pick really doesn't have so much applicability. We're resolving the bilength, we'll be able to take a very long step. Okay.
So Mikhail Ilyev asked, have you tried setting up a slow wave with an analytic solution, i.e. an ion acoustic wave or alphane wave in MHD, and seen how it behaves?
We have not yet. And I think our issue here is solving the self-consistency problem here. So right now I've shown you that it works where it works, but that was our original motivation, was in fact to solve exactly that problem. Not yet done.
And Elon Joseph asks, this seems reminiscent of transformation to relativistic coordinates with a fictitious speed of light. Have you investigated this as possible connection? Using a fictitious speed of light in Maxwell's equations can also be used to control the Debye length.
Yeah, we have tried to find out the analogies there, and it ends up being an imperfect analogy. In that, when you reduce the speed of light, you don't change the weight of the particle. You just go to a different physical system with a lower speed of light. But here, when we reduce the speed of light, our particles can still be going faster than the speed of light physically, but with beta of v, they actually just transport more slowly than the speed of light. So it actually ends up being a different thing. I don't know if that's making sense.
Yeah, I don't know. I mean, I haven't, obviously this is the first time I'm looking at things. It just it seems remarkably like there could be some similarities there, and I am familiar with this trick of modifying the speed of light, using the speed of light, modifying that in Maxwell's equations you can mock up whatever Debye length you want. So if you don't want to resolve it, you can just make it big enough that you resolve without really needing to go down to the real length, if that's sufficient for the physics of interest. Yeah, I don't know, it's just interesting. Well, thanks.
Yeah, I know, and I've thought about those things, and when we give this talk and Willie Lee's in the audience, he says, well, this looks like delta F, but I try to explain it's not. When we gave the talk and Luis Chacon was in the audience, he said, well, this looks like a coordinate transformation. And so I end up pointing out that it's not. I really think this is a different beast from those things. We've looked at them and not found a direct analogy, but we certainly agree with you that there are similarities.
And Scott Wilkes just had a question that he noticed, or a comment that he noticed the same thing, and it looked like one over beta is a lot like the relativistic gamma. It is V naught looking like C.
Yeah, and I think I've more or less answered that now.
Are there any more questions?
Yeah, I have a quick question. This is Jean-Luc Vey from Berkeley. Sorry for not typing. I'm not on an iPad, so it's not easy. So do you have a way to adjust the value of beta in a way that you can converge towards standard peak? And so this way do some convergence study that gives you confidence that you indeed converge toward the solution.
Yes, and we've done that. In fact, we have a number of tests that we've done and that's actually one of the beauties of this thing, Jean-Luc, is that you have a continuous transformation with this beta, with that V naught, a continuous transformation to regular old pig. So you could either take the same code and just increase beta and be able to handle situations with faster and faster phenomena, or you could just, of course, go to full regular pig and then handle all the phenomena too. But yes, we've done that. We do have those comparisons.
Okay, that's very nice. Thank you.
Well, thank you very much, Professor Cary, for the wonderful talk. And I invite everybody now to unmute yourselves, and we can all show our appreciation.